So what I'm talking about is some joint work with Massimo Franceschetti and Tom Rosamond. Well, Massimo has given a talk about work by the same set of authors. It is mostly about the same paper, although we're talking about different aspects of it. It is a 50-page paper at the moment, so perhaps we've got some excuse for talking about it twice. And the person who's not being represented is one of the authors, Tom Rosamond. That's my PhD student in Bath, but he did make significant contributions to this paper, even if he's not here. So, okay, so well, we've had percolation 101 a few times, and here it is again. But I probably do need to go through it rather quickly. So well, we're thinking about percolation on a general graph. I mean, I'm going to jump straight in with the general graph rather than worry about Z2. So in this case, we've got a connected graph and countable graph. So we're listing the edges, E1, E2, and so on, and the vertices, V1, V2, and so on. And then we're doing bond percolation with parameter P. So we take a random subset of the edges where each edge is retained with probability P, independently of the others. So then the induced subgraph is, I'll call that GP, at least in this page. And then, so according to C1, the component containing the first vertex. So I listed the vertices somehow, and so the component containing the first vertex, we're going to call that C1, a component or cluster containing V1, but this is an arbitrary listing, so it could be one of the others. And then we've got a probability, something which, well, is often called theta of P. This isn't fantastic notation because this thing is, I'm calling it the probability that C1 is infinite. That probability depends on the choice of V1, because this isn't, I'm not thinking of this as some regular lattice. So this probability would be different for different choices of V1. But anyway, if it's positive for one of them, it'll be positive for all of them. That's the main thing here. Because if it's positive for one of them, then if you take any other one, then there's a finite path from the other one to the first one, and there's a positive chance that they'll be connected. So anyway, there's some fairly simple argument that if it's positive for one of them, it's positive for all of them. So what we're really interested in is just whether this theta of P is positive or not, and that doesn't depend on the choice of V1. So this line here, this notation here, that this PC, critical P, that doesn't matter which one we chose as V1. So that's the smallest smallest choice of this parameter P, such that there's a positive chance of having an infinite component at a particular site, and in that case there'll be probability 1 that there's an infinite component somewhere, which people have mentioned previously this week. Okay, so so that's what I've said down here. If theta is positive, then there's a chance of 1 that there's an infinite component somewhere. By common cause.
Is it obvious if the graph is not regular?
Is what obvious?
Last line.
The last line.
If the graph is not regular, it's like a very strange configuration. Right?
Should still follow from the Kolmogorov 01 law, shouldn't it?
Why is not regular?
Doesn't matter, I don't think. If you change a finite number of edges, then it will still be an infinite component or not. So, yeah. Yeah, Kolmogorov. Okay, or we could do the same thing with site percolation. So we're throwing away retaining or throwing away each vertex rather than each edge. Apart from that, it's the same story. So hopefully I've managed to change all the E's to V's by now in this slide. That's one of the reasons I was late, was changing things like that. Anyway, we've got so this time, again, we're randomly taking a subset of, this time, the vertices. Each vertex is selected with probability P as being being included in the subset. So I'll call this G with a twiddle over the top. P tilde is induced by the site percolation process. So again, we've got the component containing some selected V1. Call that C1 tilde now, and theta tilde of P, which again will depend on V1. That's the probability you've got an infinite site percolation component. And again, you've got a critical probability, PC with a tilde over the top. Might not be the same with site percolation as the bond percolation, as we've seen earlier talks this week. The smallest P such that this theta is strictly positive. Again, this theta of P depends on the choice of V1, but the critical P does not. So then we've got some examples here. In some cases I've written these as fractions, and in some cases as decimals, and the fractions are the ones which are known exactly, as has been mentioned before, for bond percolation on Z2, for instance, or also site percolation on the triangular lattice. And there's the other ones are due to simulation studies. So there are some, and this one here, so that's a regular tree T2, where you sort of have an ancestor and that has two children, and each of those has two children, and so on. So you can do some branching process argument there. And in that case, you get the same critical value of P, both for the bond percolation and the site percolation. So there are some examples where you have the same critical value, whether you have bond percolation or site percolation. But there are also lots of examples where it looks like you have a bigger, strictly bigger value for site percolation of the critical value. So it seems that site percolation in general is harder to percolate.
The 0.34 is of course exact, not the way you write it, but twice sine pi over.
Okay, right, I see what you mean, yeah, right, okay.
You said that the decimals
Yes, sorry,
are
yeah, okay, yeah.
Twice.
Okay, I should have, yeah. Okay, so for all G, this was mentioned in Massebo's talk, that we do have the weak inequality, that the PC tilde is the site percolation one, critical value is bigger or equal to the bond percolation one. So we have seen this argument before. Basically, there's we've seen some version of this argument in Massimo's talk. But even so, I'll just mention it again quickly, that you can do some coupling where the so the way I'm talking about this is that we've got theta of P, or theta tilde of P, being the probability that you've got an infinite cluster at a specified site V1. So we can sort of just build up the cluster at vertex V1. So this is a sort of hand-drawn version of the movie that Massimo showed us, but maybe done slightly differently. The argument may be presented slightly differently, but anyway. So let's build up the site percolation cluster starting at V1, and we'll also assume that and we'll have some coupled realization of the bond percolation cluster. Did I say that right? No, we're going to build up the bond percolation and have a coupled realization of the site percolation. And first we're going to condition on V1 itself being open. So if I fill it in, that means it's open. So then I look at the first edge coming out of V1, maybe that one, and maybe that one's open. So we've got some enumeration of the edges, so we're going to look at the edges one by one, condition on not having looked at them before, and on those edges being adjacent to the cluster we have so far, the component we have so far at V1. So maybe that's the first edge we look at, and then the second edge, maybe we look at that and it's not open. So this one was open. So if an edge is open, and it says here in the argument there that next edge I just said that, next edge inspected is the first one we haven't looked at already, as long as it's adjacent to the cluster we have so far. And then if it's open, so we're getting a coupled site process, the far end point, if that's not already been considered, then we'll make that the same status as the edge. So actually when I drew this edge, I should have said the far end point, which isn't one we thought about before, will be open. And then this one was not open, so if that's the next one we considered, that one will be closed. So do it that way. And then maybe we go along here and that one is open, but we've already considered that site, so that's already, we decided that's open, well, even whichever status we gave to that one, even that was closed, then this site was already open. So in that way, we get a coupled, so maybe the edges we consider are always coming from the bond percolation cluster we already have. And it may be that so that picture isn't quite right at the moment, the way I've done it, because we wouldn't have considered that edge at all. So let's say that actually that's what this one was open. So in that case, that one would have been open. Anyway, the site percolation cluster is always going to be contained in the bond percolation cluster with this picture, because any site that's open, it must have been at the end of a new edge that was open, and therefore it's also part of the bond percolation cluster. So we've got this, that's got this containment here, and so the theta, the site percolation probability is theta tilde is less than or equal to theta. So if we're above the, so if one of them, so if this one percolates, if we're above the critical point for site percolation, then we're also above the critical point for bond percolation. Okay, well, there's some strict inequalities, as we saw in the table earlier. Often it's the case that we've got a strict inequality, and that's been proved for a large class of lattices. So, so the general result from Grimmett and Stacey in 1998 was that for a large class of lattices, which includes the dimensional lattice, we have that the site percolation critical point is bigger than strictly bigger than the bond percolation critical point. And there's some assumption in that theorem that one of the assumptions that there's finitely many orbits under graph automorphisms. So that assumption is not going to hold for the sort of things we're going to be thinking about, which is some kind of continuum percolation graphs where, for example, for that you need to have that bounded degrees. So the vertices, if you've got a lattice, then, I mean, if you've got something like Z2, then everything has degree 4. So more general lattices, you've still got some, maybe more complicated with, it's got finitely many orbits, then everything is in one of these orbits. So there's only a finite number of possible degrees that the vertices can have. But if we're going to be looking at continuum percolation graphs which have unbounded degrees. Okay, so there's the basic model of continuum percolation then, which we'll start by thinking about as being the basic case of the results we want to talk about, is the so-called Gilbert graph. So for that one, we've got a homogeneous Poisson point process in R2 with intensity lambda, and I probably didn't need this explanation of what a Poisson process is here, but anyway, it's the number of points in in disjoint regions or independent Poisson variables with parameter given by lambda times the area of the region. So we've got points scattered around randomly in two-dimensional space in the plane, and we're going to form a graph on these points by joining them whenever the distance between them is less than or equal to 1. So here's our Poisson process, and say the distance, maybe all these guys get joined together if the distance is less than 1. And you might imagine that if the Poisson process has a high enough intensity, then there's a chance that there will be an infinite component in this graph. So this, and that is indeed the case. So this result, this is a basic, well-known result about continuum percolation, that there's a critical value of lambda such that if lambda is less than, and in fact it's known for this graph, less than or equal to the critical value, the fact that this, then it doesn't percolate, and if lambda is bigger than that critical value, it does percolate. And again, there's some kind of Kolmogorov-01 law or ergodicity argument that says this probability must be either 0 or 1. The fact that it doesn't percolate when lambda is equal to lambda c is due to Ken Alexander. Okay, so if we're above the critical point, then we do have an infinite component, and in fact it's known as, there's analogous results in lattice percolation, we know in this continuum setting that we have a unique infinite component with probability 1. So the first theorem, which naturally calls it theorem 0, is that if indeed lambda is above the critical value, then the critical PC, the bond percolation critical point, is strictly lower than the site percolation critical point. Yeah.
Could you say what is the answer for inverse? For given lambda find R such that the field percolate?
Say that again?
Okay.
Oh, given lambda find R.
So find R,
Yes, well there will be a critical value of R such that it,
well, of course it's equivalent more or less.
yeah, it's more or less equivalent.
But it is,
And there is an interesting paper also by Ken Alexander from around the same time about simultaneous uniqueness of the infinite clusters in that setting. Okay, so that time being the early 90s, I can't remember exactly. Okay, so so we form this graph. We're assuming lambda is big enough that you do have an infinite component, and then you know you have a unique infinite component. So we are effectively doing percolation on a connected graph because we can just forget about all the bounded component, all the finite components. So we've got a single infinite component, and we're doing percolation on that. And then we're saying that we do have this inequality holding. I should point out that in principle these things are random variables, these PC of G lambda. It depends on the realization of the Poisson process. But again, there's some kind of ergodic or station. The ergodic property of the Poisson process, it's stationary under this so-called random variable is stationary under translations, and by the ergodic property of the Poisson process, that means it must be almost surely constant, or there's a version of Kolmogorov's 0-1 law that can be used to demonstrate that in fact this thing, although in principle random actually has variance 0, so is in fact constant, so that these are just two numbers for which we have a strict inequality. I called it theorem 0 because it's going to be a special case of theorem 1 coming up. Okay, so that's the first result, and we'll say a bit about the proof of that later on. A more general version of this Gilbert graph here is to connect points together, not just sort of say yes or no and that they're connected if the distance is less than 1 and they're not connected if the distance is greater than 1, but now to say that the probability they're connected with some probability that depends on the distance between them. And I'm actually going to say it's a decreasing function or non-increasing function of the distance between them. So the closer together they are, the more likely they are to be connected. So we're going to have something we call a connection function f, taking values in the unit interval, and that's so f of x minus y, or f of the distance between x and y, represents the probability that points x and y get connected.
And you're doing it independently.
Sorry?
And you're doing it independently for different pairs, I see.
We are indeed doing it independently for different pairs, which I didn't. Consistent with my presentation of bond and site percolation, I haven't mentioned that, but that's true. Okay, so so given lambda, we've got now a graph G lambda f. So the vertex set, which I'll call V, is the Poisson, the realization of our Poisson homogeneous Poisson process with intensity lambda, and now the probability we join two points is this function f of the distance between them. So if the function f was just like that, a step function, then it would reduce to the Gilbert graph, because then you'd be joining with probability 1 if the distance between them was less than 1 and not otherwise. So I've said that somewhere here, I think, down here. But in general, we might have some function that might be horizontal for a while and then decrease or whatever. So we're going to make some assumptions about this. So the first assumption we're going to make is that it's integrable. So I put in a lambda here because then you get this integral then f of mod x dx becomes the expected degree of a typical vertex. So what do I mean by typical vertex? Well, in the case of a Poisson process, we could think of this as just conditioning or having a point at the origin, say, or in an infinitesimal region around the origin, and then by the independence properties of the Poisson process, that doesn't, you've still got a Poisson process outside of that, and then the probability of having a point in a volume element dx is lambda times dx, and so if you sum or integrate over all x, this gives you the expected degree of this inserted point at the origin, representing a typical point. So this is the expected degree, and you might imagine that if this integral was infinite, then there's going to be lots of vertices with infinite degrees, and in that case, percolation isn't, I mean, it's always going to percolate. So, so we're not going to think about that situation. We're going to assume this integral is finite, but also the function shouldn't be everywhere 0 or almost everywhere 0. So that's some reason for that. Otherwise, you wouldn't have any connections at all. Okay, so I said we're going to take, I don't know if this is actually necessary for everything I say, but anyway, we're going to assume f is non-increasing. It's a function of r. And then we're either going to assume that in fact the f has bounded support, so it could either be the step function I mentioned before, or anyway something that eventually hits 0, some function that hits 0, or if it does remain positive, then in fact this is a technical condition that would be nice to get rid of, but it appears in the proof, that it doesn't decay too fast. So f of r equals e to the minus r is okay. This thing doesn't decay too fast. F of r is e to the minus r squared. It's not okay.
If you wanted to do something like a normal scale, you could do special cases like that.
Maybe we haven't tried. Yeah, I don't know. Yeah.
Essentially, it's a condition of regular variation to some extent.
Something like that. Yeah. Okay, so we're going to assume that about that technical thing about the f throughout. Well, in fact, when it comes to the proof, I'll just be talking about the Gilbert graph anyway. But so if we're given such f, then there is a critical value of lambda. So this is just still this part is just presenting the basic theory of the random connection model. Can be found in Mathew Penrose's book on continuum percolation, for example. That there is a critical value lambda f. So we're now given the f. So the connection function is specified, and then we're thinking of we can vary the lambda, the Poisson intensity, and if it's big enough, given such f, then we can find there is some critical value lambda, such that if lambda is above that critical value, then there is an infinite component, almost surely, and if it's below the critical value, there is no infinite component, almost surely. In this case, I haven't mentioned the case of lambda equals lambda f, so I've had a few holy grails mentioned this week. So, well, I would think that there might be some way to make Alexander's argument work for more general connection functions. So, in fact, this extends to lambda equals lambda f, but I don't know of anyone having done that.
There's an example where it is discontinuous.
You're saying that
There is a counterexample.
there's a counterexample. Okay, does it have infinite support? Okay. Okay. Okay, well, that's why I mentioned these things, so I learned about examples. Okay, so, okay, and this is also in Mathew Penrose's book, that if there is an infinite component, then it's unique. Okay, so so this theorem 1, as I mentioned, is going to be a generalization of theorem 0, that assuming we are indeed above the critical value for the particular choice of f, in that case the bond percolation critical point is strictly less than the site percolation critical point. And again, these things in principle are random variables, but again, in fact, they're not. There's variance 0, these PCs. So, so this is just two numbers, one of which is bigger than the other. Okay, so the technique, so I'll say a bit about the proof of this later on. A somewhat related, well, quite closely related method of proof gives this further result, which says that if you change if you've got two connection functions f and g, and f dominates g somehow, so it might be that this is connection function f, maybe the function g is, well, it's just multiplying by f by a constant less than 1, so maybe that's the connection function f and that's the connection function g. So the connection function g is less than f, and in fact, as long as it's less than or equal to f everywhere, and it's strictly less than f somewhere, then we have that then there's some easy coupling to show that the lambda c of g is greater than or equal to lambda c of f if it percolates with the f connection function. Is also say that wrong way around. If it percolates with the g connection function, it also percolates with the f connection function. That gets greater than or equals, but again we can get a strict inequality, and that takes some work along the lines of probably slightly easier, but somewhat similar to the proof of this. That you have the strict inequality. As long as g is less, well, what I said, g is less than f, strictly less than f somewhere, and less than or equal to f everywhere. And the reason for including that is that both theorems 1 and 2 are needed to prove theorem 3, which Massimo talked about quite somewhat in his talk, so let's go through this pretty quickly. That if you spread out the function f, so you compare two connection functions, one of which maybe is just a simple step function, but the other one is a spread out version of the step function, which has the expected number of connections is the same, but because on average there are more connections at a greater distance, then there's a strict inequality between saying that the spread out version is better. So the critical value of lambda, better in terms of more likely to, better chance of percolating. The critical value of lambda for the spread out function f, so this is the function f, and this is the function SPF, and it's supposed to be spread out in such a way that the expected number of connections are the same. That the critical value for SPF well, let's just think about the case with p primed equals 1, is less than the critical value for f. Okay, so that was mentioned in the talk, and it was also mentioned that it's known that this limiting behavior as p goes to 0 of the critical value as well. But okay, so that's, I mean, we've heard mentioned that that's a nice fact that that we're getting as a consequence of theorems 1 and 2, that we have this sort of idea that spreading things out while keeping the average degree the same helps you. It improves the percolation properties. So that's a nice thing to deduce, and that's something which seems to be particular to the to this continuum percolation model, whereas we get
essentially just have a branching process. Then is that
that's the intuition behind this result here, is that yeah, that's okay. So we get a conclusion here that's particular to the continuum. Don't know of a lattice analog, whereas we're getting that from a result which we could say, well, that's just something which you'd expect because it's known for lattice percolation. Okay, so we're going to say something about the proof of mainly of theorem 0. So that was the one for the Gilbert graph where you just connect points at distance less than 1. So that uses this enhancement technique, which Massimo did mention, without saying too much about. Well, I mentioned a paper by Grimmett and Stacey from 1998, and as Massimo mentioned, there are some earlier papers, Menshikov in the 1980s, Eisenman and Grimmett 1991, have also used this technique. And in fact, there have been, it's been applied in quite a few other places as well, versions of this technique. The arguments we're presenting here do, as I say, this is for a lattice setup, so we're going to have to do some adapting of these for this continuum setup. Okay, so we're considering the Gilbert graph then, because it's theorem 0. And we're going to somehow, what the enhancement does, it's saying that there it is. No, it isn't. I've presented some kind of argument why the site percolation is dominated by the bond percolation, and somehow if you can do a little bit of an enhancement of the site percolation where you sort of add a few extra open vertices, and it's still dominated by the bond percolation, and then if you can then show that that the enhancement strictly changes the critical point, then you'll be able to get the strict inequality. So how's the enhancement going to work in this particular case? We're going to say that a vertex in this Gilbert graph is correctly configured if this is the restriction of G to V, a particular vertex V, and its neighbourhood in the graph. So the neighbouring vertices is a bow tie figure as shown. Well, when I say as shown, I mean as I'm going to show by drawing it on the board. So there's a nice bow tie. So this is supposed to be part of the Gilbert graph. So there are various edges elsewhere, but this is V. It's got these four neighbours, and they're joined together, forming these two triangles, like that.
So it is assumed to have degree 4. You can't have other bows coming off.
We're assuming, yes, there are exactly 4 vertices in the neighbourhood of V. So then the enhanced site percolation model we're going to talk about is going to be, the original site percolation is just going to be what I'm calling red vertices. So I'm going to colour vertices red with probability P, and then we're going to enhance a vertex if it's in this correct configuration and all its neighbours are red, but it is not. And so if these ones all happen to be red, and this one is not red, then the enhancement will sort of toss an extra coin for this vertex, and with probability, an extra probability we'll call Q, we'll say that's green. So if I probably use colour here somewhere, but anyway, this one's going, it's not bother with colours, so I'll say this across, say that represents it being green. So that's adding a little bit extra to the original site percolation model. And then the subgraph induced by all coloured vertices, red or green, I'll call that GPQ, at least for the duration of this particular page. Okay, so then an enhancement lemma, so something like this is in the earlier literature on the lattice type arguments, enhancement arguments. For any graph, there exists, if there is some p which is below the site percolation probability, so we're thinking that the bond percolation ought to be able to percolate at a lower p than the site percolation probability. So if there's some p which is subcritical as far as site percolation goes, such that if you enhance with parameter q equals p squared, then this is the bond. So if the enhanced thing percolates, the enhanced site percolation percolates, then the bond percolation also percolates at this parameter p, which is less than the pc. So this is saying the bond, this is a theta without a twiddle, so this is the bond percolation percolating, that happens. So in other words, p is greater than or equal to the bond percolation critical value, and therefore the bond percolation critical value is strictly less than the site percolation critical value, because we assume the inequality, strict inequality for the p. So we do the same kind of argument, same kind of coupling argument I mentioned before for the proving that PC bond is less than or equal to PC site. So again, we grow C1, that's the cluster at our starting vertex, whatever that is, in the bond process. So C1 is the cluster at V1 in the bond process, inspecting edges in turn, starting from V1. So we couple the red site process in the same way. So the same kind of thing as before. Maybe this edge is open, so we include that one. Maybe this one is not open, so we don't include that one. This one is open, and so then somewhere we're going to have a bow tie. This will happen from time to time. We get something correctly configured, and then maybe we actually decide this one is not open. So in that case, this is not red, whereas these ones are all red. Well, in that case, we've just examined one of the edges so far that comes into this vertex. And then we're going to say this thing is green if we have to label these somehow. So I'm thinking this is W, this is V, W, X, Y, Z. Then there's going to be another one from this side of the bow tie, and we're only going to say it's green if this one is open and this one is also open. That's the only way we're going to say it's green. So we have some other shots at this vertex, and well, so that means that it means that we can get to this. So if we do end up making this one green, then we must have visited this. This one must be red, which means we must visit it by some route. It must be part of the site percolation cluster. So this one must be red. So we must have visited it at some point. So this part of the part of the bond percolation cluster, and then because we're not going to make this green unless this edge is open, then we must have this must also be part of the bond percolation cluster. So at some point we're going to inspect these edges too, because this is part of the bond percolation cluster, and then we're only going to at this point it was only provisionally green, but once we've looked at this edge, well, maybe it actually is green. but we have to, but only if this edge was open as well. But in that case, then we've actually got this vertex is part of the enhanced bond percolation cluster, or that might use this green vertex. Sorry, the enhanced site percolation cluster that might use this green vertex, but it's all contained in the bond percolation cluster. So so we've still got this, call it C1 hat. That's the enhanced site percolation cluster of red and green vertices, starting from V1, which is contained in the bond percolation cluster, and then then you've got the same sort of inequality as before. So that gives us that if it if the site percolation process the enhanced site percolation process percolates, then the bond percolation one does as well, which is what we're saying up there. So if this thing is strictly positive, then this thing is also strictly positive. Okay, so that's the general idea of that part of the argument. As I say, that is seen in the other, or something like that is seen in the other literature. So something which, some things which are slightly different. Well, this is. Okay, so now we're going to think about if it percolates, if you go off to infinity, then you must be able to get from the centre of a large ball or disk to the boundary of a large disk. That's more or less what this is saying. So notation BR is just a disk of radius r, centred at the origin, and the boundary of that, I'll call that the boundary is going to have thickness a half. Thickness has to be half, not 1, for technical reasons I might mention later, but anyway, that's a bit of a technicality. And we're going to have also a ball of radius a half, rather than 1 in the middle, and I'll say that AN is the event that you can get a coloured path from the middle of the from the middle of this large ball of radius n to the boundary. Well, probably pretty obvious, but so there's going to be a coloured path from the middle of this ball to the boundary. We're only using here. We're doing an enhancement only with. This is something of a technicality, but anyway, we're only using the enhancement. We're restricting the Poisson process to the disk, to Bn. So we're just forgetting about the points outside, and any enhancement that takes place, deciding whether something is correctly configured, we just look at its neighbours within the disk of radius n. So then there's a lemma that if the enhanced site percolation process percolates if and only if the limit of this theta star is greater than 0, where theta star is the probability that there is this coloured path. And these things aren't exactly because the enhancement, the possibility of enhancements from outside or extra vertices appearing outside which weren't there before, it's not exactly monotone. So, I mean, morally speaking, then there's sort of monotone convergence to the probability of a path to infinity. But there is, in fact, a bit of extra work to be done, because this is, although one would expect this sort of monotone convergence as n goes to infinity to the probability of a path from v0.5 to infinity, that's not, it's not straight inclusion, but one can adapt the proof that it's close enough that one can make it work.
Sorry, are you on Gilbert graph now or random dimensional?
Gilbert graph, yeah. Okay, so then an ingredient in some of the other, well, in many arguments in percolation is the Rousseau formula. This in continuum, or in this particular version of continuum percolation, this enhanced version of continuum percolation, it says the following. It says something about what happens if you differentiate with respect to p the probability. So we've got this theta n as the probability something like this happens for the enhanced model. We've got these two parameters, p the probability of colouring it red and q the probability of colouring it green if it happens to be correctly configured with red neighbours. So you can think about differentiating with respect to p or with respect to q. So the Rousseau's formula, well, more commonly seen in the lattice process, is saying that, well, if you, basic idea of this is that, well, if you slightly change the percolation parameter a bit, chances are then if it changes anything at all, it'll just make one site open when it wasn't open before, and so and that'll make this increasing event happen when it wasn't happening before if that site is pivotal. And so pivotal means that the event we're interested in happens if that site is open and doesn't happen if it's closed. So in this case we've got two forms of pivotality. We've got pivotal with respect to red or pivotal with respect to green. So it's one pivotal, that means the red pivotal. That means if you take the enhanced model on the Gilbert graph restricted to the n disk radius n, and then you add a point at x, and you decided on the colorings for all the points except the one at x, then if you make x red, the inserted point at x red, then it does happen, and it doesn't happen if it's not red. And green is the same thing, only with regard to making it green. P2 pivotal is with regard to making it green.
Matthew, actually Rousseau's formula was proved several years earlier by Grisha Margulis.
Yes, I can.
Only it was in Russian, so.
Right.
Yeah, but if you know, then why don't you call it Margulis-Rousseau formula? Either Margulis formula or Margulis-Rousseau. What is illegal is Rousseau.
Illegal. Okay.
It's completely unfair.
There may be someone before Margulis, who knows? I don't know.
Completely unfair.
And most of the terminology is completely unfair.
No. But once it gets known that it's unfair for a while, but when it gets known to be unfair, then it gets corrected.
Okay, I take it back. I did not know it was due to Margulis. I was aware that it was in books and things before Rousseau's book, but I didn't have time to check back through the literature to find exactly who proved it, so I'm sorry. Apologies for that.
That was in Russia. So.
Okay, and I didn't have time to learn Russian either. So where was I? Okay, so if you change with respect to p, then loosely this formula ought to say that the expected number of vertices which are pivotal in the sense in the red sense or in the green sense is the number of is the derivative. In this continuum setting, then you have to know what this thing here is just the expected number of pivotal vertices in the red sense. This is actually an example of the formula which Günther Last mentioned in his talk. This is probably also misattribution. But anyway, he called it, I think, the Mecke-Slivniak formula, or Halm theory for the Poisson process, or whatever you want to call it. But anyway, so the expected number of points which have a certain property in a Poisson process, then you could lambda dx is the probability you have a point in a particular volume element, and then given that you have a point there, then the chance that it's pivotal in the first sense is given by this thing here, given by Pn1, because that's the probability an inserted vertex is pivotal. So anyway, this is the derivative with respect to p, and this is the derivative with respect to q, both the same formula. Okay, so then the key lemma is that the probability that it's two pivotal, the ratio between the probability of being two pivotal and the probability of being one pivotal is strictly bounded away from 0. With this lower bound being, it depends on p and q, but in a continuous way, and it's strictly positive for any given p and q, which are in the unit square. Okay, so that's, that bit of discussion is needed on the proof of that, but maybe we should just go to the, let's say if we accept that bit of the argument, then we can follow some similar argument to what was contained by Grims and Stacey. By the way, I noticed there are a lot of streets in this part of Cambridge named after great scientists like Clerk Maxwell or Charles Babbage. Anyway, there is a Stacey Road nearby. I don't know if it's Alan Stacey. Anyway, there's the similar argument to what they do. Well, I mean, I won't go through this, as I say, because in some sense it's not specific to our paper, but you've got these parameters p and q, And if you've got PC, this is supposed to be PC site, so I'm supposed to have a twiddle over it, then you know that you do percolate if you're slightly above PC, and then if you reduce, this is supposed to be Q, if you reduce P a little bit, then you can compensate by increasing, sorry, if you reduce P a little bit, then you can compensate by increasing Q a little bit. And what that key lemma said before is that you really can compensate because of the ratio of the partial derivatives. You really can compensate by increasing Q a bit. So you can get to a P which is strictly less than PC and a Q which is equal, let's just say, to P squared, such that you're below PC and you've got this extra Q, and because you percolated at this point, then you still percolate at this point, but then we're done because we can use the old enhancement lemma that we've got P below the PC where we're enhancing with probability P squared, and we're still percolating. So here we're also percolating as well. So that's loosely what this part of the argument says. So then this thing we need to try and prove is this ratio between the two P's being strictly positive. Okay, so the general idea is that if we know that a site X is one pivotal, so we've got this picture here, but now we have to perhaps think about so let's think about some site which isn't too near the boundary or too near the origin. So this is our X, and then we take a ball of some fixed radius, something like 30, around it, and if it's one pivotal, that means somehow that there's a path from here to the boundary, but not like that. It has to actually pass through X, because it has to be that adding a red point at X makes you percolate, whereas you wouldn't have done otherwise. So if it's one pivotal, then in fact you must have some picture like that, with this path actually going into X. So then the general idea is that you can resample the Poisson process on a ball of radius 30 around X. That's this disk here. The probability that it becomes two pivotal, well, so the idea is that should be bounded away from 0, and then this is just resampling on a finite region, so this thing doesn't depend. I mean, sort of key part of this lemma is that this delta doesn't depend on n or x, so it doesn't matter how big the disk is we're working on or which part of the disk we're working in. That's part of the reason for having radius a half rather than 1 as the thickness up here, by the way. Okay, so it's a bit more complicated than that. You can't just, as it turns out, you can't just resample on a fixed radius b30, because it might be that the last point before you reach the boundary was sort of distance just very close to the boundary, sort of distance 0.999 away from this boundary or something like that. So you have to do a bit more work, which sort of extra work which doesn't arrive in the lattice setting. So in fact, it's a resample on some, well, gone from 30 to 25 for reasons I might say in the next slide, some stopping time. So you sort of build your process. So you've got to, now let's think of this as 25 instead of 30. We've got our Poisson process outside this, and then we build it up inside until the first time we hit a new vertex that's attached to this path to the origin, or to near the origin. And that's a sort of stopping time, and then we don't know what's happened further inside than that. So that's the general idea of this, but you have to also worry about building in from the path to the boundary as well. And there's some extra complications due to the greenness and the redness coming into things. We've got red, and they're sort of more or less talking about the red vertices then, but actually got some green vertices as well. So this is a sketch of how one deals with those extra complications. En1 is the same as the original one pivotal event, that X is one pivotal, more or less, except that now we're also going to say that everything is red inside B30. Well, that is possible. The probability of that happening divided by the original one pivotal probability is bounded away from 0, essentially because in a bounded region there can only be there's only a finite density of green vertices in here, and sort of conditional probability that in fact all those green ones were red is bounded away from 0. So that's sort of the basic reason for that statement there. So we're going to expect the whole Poisson process outside B30 and then the red Poisson process in the annus of radius between 25 and 30. So that's the first technicality which can lead us to forget about the green, the extra green enhancements. And then V and T, well, V is this stuff that's connected to the origin, and T is the stuff that's connected to the... So now if I blow up this picture here, maybe I've just got a single vertex in V, which is near the boundary. This is B25 now, of X. And we've got a vertex T, which is, so this one is going off to the origin, near the origin, and this is going off to delta Vn. And then we've got regions like that. And then we build inwards until the first vertex we see, which is joined to that, and then continue to build inwards in this region until the first vertex we see, which is close to that. And that's the stopping time I was talking about. And then we resample in everything we haven't considered already. And having got to that stage, we've got two vertices near the boundary of whatever this region is, and then we can sort of create little paths to give us a bow tie in the middle. We've got one, this is going off to the boundary, this is going off to the origin, and if we've got Poisson points in each of these regions, in each of these, just a single Poisson point in each of these circles, and nothing else in this disk, then we'll get them, and these things are all red, then we'll get this point being too pivotal, and that's something with probability bounded away from 0 by some ridiculously small constant, but as long as it's strictly positive, we're okay. So that's resampling. In the remaining unscanned region is everything except for the stuff we've already looked at, which is everything outside. Something like that. Everything outside this big circle, and also this little shaded region up here. Okay, so that's the probably more detail than you needed to know, but anyway, that's the, part of the argument for the proof for the Gilbert graph, and then there are quite a lot of extra complications due to thinking about the more general random connection model, and various different cases have to be considered separately. But luckily, we're out of time to go into that. So, thanks very much.
Okay, any questions?
Suppose that you have a sequence of kernels such that integrals of n tends to infinity. Then asymptotically you approach a funny world where the percolation sense of things in cluster is completely not the same as percolation of the mean size of the cluster. And what you expect to see?
Can you say that again? Sorry.
Suppose you have function f.
Okay.
Integral is finite, that's fine.
Yeah.
Suppose you have a sequence of functions.
Sequence of x. Okay.
And integral tends to infinity. Then asymptotically, you approach the situation where the percolation is the sense of mean size of the cluster is not the same as percolation is the sense of existence of the cluster. And what kind of picture you expect to observe in this system? What is the intuition?
Not sure I have a good answer to that one.
Because clearly that if you just take integral as finite, then there's several senses of percolations. If the integral is finite, that's more or less obvious.
Right.
Then of course percolation is in the sense that if cluster is finite, it's not the same as you say the size of the mean size of the cluster is finite. It's clearly different things. But suppose you approach to this kind of model, what picture you would naturally expect?
Yeah. Picture of what?
Okay. what configuration? What is the intuition about? Is there the limited case?
And there are some limits.
Percolation can be a different sense.
Yeah, there are
If
some.
integral is infinite, you can have a different sense of percolation. That's more or less obvious.
Well, there are some results. I don't think this is answering your question. There are results about high density that what the remaining finite clusters look like in high density, but I don't think that's quite what you're looking for today. We have to discuss it later. Right.
Critical points.
Yes, of course, critical points will be different, of course, in the limited case. That's more or less, I don't know how to prove it, but that's
It's really clear. Let's we can continue the discussion afterwards. Sharp.
The assumption you have on your function f is that the infimum of either it is bounded or f, the infimum of f of r plus 1 divided by f of r is the lower bound.
Yes.
So it's extreme.
So if it has a power law or an exponential, it's okay. But
Yeah.
if it's Gaussian, it's not okay.
That's right.
Exponentials,
Can you explain that? The equations to
Well, not very well, but it's something that comes up in the proof. Somehow you'd like the probability of being of having connections to the origin from a long way away to have some control over them. And well, at some point in the argument, we've got a series of annuli and using that condition, then you can have some control over the probability that the origin is connected to any of these annuli. That's not a very good answer. I'm sorry, but that's the best I can do.
Any other question? Okay, so then let's thank the speaker again.